The following podcast is sponsored by Structure Tech.
We talk about old homes and how they tend to really dry out in the wintertime. Mm-hmm. It's because you're constantly replacing that warm, moist air with dry, cold outdoor air. It dries a house out really well, and it makes your house really durable, too. I mean, we talked about that at the last episode about what makes a house durable. This is a durable home.
Welcome, everybody. You're listening to Structure Talk, a Structure Tech presentation. My name is Bill Ulrich, and I'm alongside Tessa Murray and Ruben Saltzman. And if you've been tuning in, you heard our last episode about new houses versus old houses, and we thought we would cover more ground than we did in those 25 minutes, but unfortunately, we still had some things that needed to be talked about.
I kind of hijacked that to talk about, we nerded out.
Well, it's okay. It was mostly about construction technique and what these boxes look like, but I wanted to ask some questions about how these buildings feel. I know how my 1941 house feels.
How does it feel in the sustainable urban core in your old house?
Well, it's quite comfortable when you have the thermostat at 78 degrees. But when you're down around 68, it's less comfortable. That had a lot to do with how the HVAC system was designed.
Yeah.
But, so, Ruben, Tessa...
Air quotes, designed. More like put in.
Thrown in, yeah.
Sure. So tell me how things evolved over when it comes to indoor comfort. The trunk of my HVAC system basically goes up the center of my house like an elevator shaft. We don't see that anymore when we're in houses.
Yeah.
So tell me about the evolution of that.
Well, it all started out with gravity furnaces. You'd have this big flame down in the basement, and it would connect to the ductwork, and you'd have warm air rising up through the middle of the house because, as we talked about on the last episode, warm air rises, and you'd have this warm air just pumping up to the upper levels, and then it would go across the room, and as it reaches the outside walls, it would cool down significantly. You might even have unheated outside walls. It would really help to cool down that air, and then it would fall down the returns, which would be located at the exterior walls, or, well, technically on the floor, right by the exterior wall. And so you'd have warm air coming up the middle, cold air falling down on the sides. That's the way we had with the gravity system. But
in that return was not ducted. It just was a hole through the floor, correct? Or were there ducts set up in the original gravity?
You could have both. You could have both.
Okay.
You could have holes going down in the basement, and you would also have return ductwork going directly into the furnace. You'd have both. Okay. A lot of the time, in fact, you know what? I don't see a lot of holes going down into the basement. I think if I ever do see a hole going into the basement, somebody screwed up. That was a homeowner messing around with their house. Something you would have intentionally, though, is a hole going from the second floor down to the first floor. And then, if you're on the second floor and you look down, you can wave at the people walking around on the first floor. It's like it was wide open. You just have a little grill over the top of that. That was intentional.
Okay.
Yep.
Okay. All right. So then what happened? Did the light bulb go off?
Well, our heating systems got more and more efficient. And like what Ruben's talking about, those gravity furnaces or, octopus boilers, those were like 50% efficient?
Yeah,
50% of that available heat went up the chimney instead of being used to heat your house. So flash forward, now we have furnaces that are 90% efficient or greater, and they're condensing furnaces and they vent out the side of the house. Instead, now we have systems where, you've got that, energy efficient furnace, and you need to have a designated supply going to every room that takes the heat and a designated return. Now, you don't have to have a return in every room. There's ways around that. Builders can do a pass-through grate above doors for bedrooms or undercut doors for a central return.
That, Tess. The first time I saw that, I remember I was not happy. It was a new construction home, and I'm looking at this, and they got a big return on the first floor, like this grill the size of a furnace filter. It was like 16 by 20. 16 inches by 20 inches.
That's what I have in my condo.
Yeah. And I see this, and it's new construction. I'm like, no, you cannot do that. You need returns. Something's wrong here. And I ended up calling the building official for the city saying, how could this be? You can't do this, right? You guys already signed off on this, but how? Why? What? And they're like, there's nothing in the code that says you need a return in any room.
Right. Yeah.
And so I was glad that I didn't, make a you-know-what out of myself by telling the client this is wrong.
Yeah.
I just thought it to myself, and I made some phone calls to verify.
Yeah.
Your animation suggests you still aren't in agreement
He's whipped
with
up
this
about
technology.
I don't like it. I mean, what does that do for your air conditioning? Think about how an air conditioner works. It doesn't work by pumping cold air into a room. It works by removing heat from the room. I'm doing a lot of hand gestures. I know it comes through well on this podcast, but I'm pulling the heat out of the room with my hands. That's how an air conditioner works. It removes heat. It takes warm air, passes over to the evaporator coil, and distributes air with heat removed back into the room. Now, if you have no grill to take that warm air out of the room, how's this supposed to work? And I'll tell you, it doesn't work well.
Yeah. In theory, it's supposed to work if you have one of those pass-through grates, above a door, like to a bedroom, so that air can move from the bedroom to the hallway to eventually to get to that central return. Or if you don't have that pass-through grate, the doors need to be undercut so you have an airspace so that when the door is closed, you still have that central return that can suck the air out of the bedroom. But like Ruben said, a lot of times it's not very functional.
Yeah. It's not to say it's not going to work. I
Yeah.
mean, people can still be comfortable in homes that have this.
Yeah.
It's just not as efficient.
Well, and the challenging thing is too with these new houses and having a system that's a lot more energy efficient, and there's a fan that, we're not relying on just that big flame to warm the air and that warm air to rise and heat the house naturally. We're relying on a system that has a blower and a fan to kind of push and pull the air through the house. And so properly sized ductwork and location of supplies and returns all really play a big part in comfort in every room of a house. And there's calculations that should be done by an HVAC contractor to figure out what size those supplies and returns need to be, how many supplies and returns a room needs based on its size, and the manual J calculations. But who actually does those?
And even for the people who do them, how many are actually doing them right?
Right.
None of them.
No.
What does a manual J, what is that? Is that literally the manual that explains how to do this calculation?
No,
Or
it's
I've
like
heard this before.
it's engineering. It's like a program that does the engineering to figure out sizing and installation for
Yeah, and it's going to take all
HVAC
kinds of
systems.
stuff into effect, like, square footage, the amount of exterior wall area, how many windows, the U value of your window, the insulation. I mean, it takes everything into effect, and it figures out how your house is all going to be comfortably balanced and what size system you got to have and all that. And if people actually followed that, all of the rooms would be the same temperature and everything would be nice and comfortable.
Yeah.
But
Yeah, if all the inputs into the program are correct and the person actually installed a system that was actually designed for that properly, it'd be great.
But what happens when you put garbage in, Tessa?
Garbage out.
That's right.
All right. Well, okay. So I hope I didn't offend any manual J calculators out there for my lack of understanding what that is.
Good.
But I should also say that this conversation has really been about forced air delivery systems.
Yeah.
The old houses with the radiators that are out at the walls, those can
Yeah.
be very, very comfortable.
Yes.
There's just no air conditioning in most of
Right.
those houses during the summer unless you've got a really special add-on package after the fact.
Which you bring up a good point, Bill. Radiant heat is, I think, some of the most comfortable heat. You've got forced air, a furnace, it kicks on. It's like, a blast of hot air, right? And it can be loud, and then all of a sudden it turns off, and then it gets cold again. With radiant heat, it's just this nice kind of cozy warmth coming off of a radiator, right?
Yeah.
I think it's comfortable.
Doug Hansen, author of Code Check, you never got a
Yeah.
chance to meet him, you guys, but when he'd teach seminars, he'd call him, "Oh, you mean a scorched air system?"
Scorched air
Okay.
He hated forced air systems.
But the thing about these older houses with the radiant heat, that's great. But if you want to add central air, you got to install
Ductwork
a
at some
ductwork system or some other system, or you could do a mini split system.
We can talk about that. We're going to step away and take a break. You've been listening to Structure Talk, a Structure Tech presentation.
Hi everyone, Bill Ulrich here with Structure Talk. Do you live in a home that has a homeowners association attached to it? Here's an interesting nugget. In 2019, Minnesota passed a law that requires all HOAs have a preventive maintenance plan in place. What's that, you say? I know, right? And what's necessary is clear as mud. At Structure Tech, we put together an affordable solution to help HOAs meet this obligation. If your association isn't talking about this, they should be. Check out how we can help at structuretech1.com. We've been working closely with management companies all year to come up with a win-win-win to meet this new requirement. Let us know if we can help at structuretech1.com.
Welcome back, everybody. You're listening to Structure Talk, a Structure Tech presentation. My name is Bill Ulrich, alongside Tessa Murray and Ruben Saltzman. And we were just talking about old houses and radiant heat at the back half of that first section. We're going to take a right turn now. And Ruben's got a question that he has had his hand in the air for a while over here for Tessa when it comes to old houses.
So the last thing, Tess, you're talking about manual J calculations and the importance of proper duct sizing and all that to get air where you want it. What happens on these old houses, because really our topic is old versus new. What happens on these old houses when we convert from a gravity system to a forced air system? How do we get all that ductwork properly done? And what actually happens?
That's a great question. From what I know should be done scientifically is that ductwork needs to be resized. You can't just use all of that existing ductwork because that was meant for a gravity system, and now you're going to a forced air system, so it needs much smaller ductwork. So it'd be ripping it all out and installing new stuff and installing more supplies and more returns everywhere.
But that's never happened, right?
I've never seen it happen.
Yeah.
Never seen it happen in a
Feels
retrofit.
fairly invasive if you're going to
It would
really
be.
do it right.
Yeah, it would be.
You end up taking the supply registers, converting them to return registers, and then you run smaller supply trunks inside of the old returns. That's it.
Have you seen that?
It works well enough.
Yeah.
I'm having a hard time visualizing what you just said, so dumb it down for me.
Well, on a gravity system, you've got these big supplies that run right up through the middle of the home. Now, all of a sudden, we turn that into return. That's air that comes back into the forced air furnace.
Okay.
And you have supplies going to the outside walls. And they use those return chases, except they run ductwork inside of it because it's much smaller now. Now it's under pressure.
Very good. Now I understand. I thought you were saying they were both living in the same space. Okay. I'm cool. Moving on.
All right. So next topic was indoor air quality and changing out the air in the home.
Yeah.
Really important thing.
Well, when you start messing around, new houses have this, they're thinking about this right away, but these old houses, when you start converting, and how do you manage indoor air quality on this old house that's leaky and maybe doesn't have great ductwork?
Yeah.
And
Well, the thing about building science is, a house is a complex system, and all these components and systems are related to each other. So when you change one thing, you can cause unintended consequences in another area of the house. And part of that is if you tighten up the house and you do air sealing in the attic, or let's say you want to beef up the insulation in the attic or add insulation in the walls, you make that house a lot more energy efficient. It has higher R value. It's leaking less air, right? You do all those things, you improve your energy efficiency, maybe you improve your comfort, but now you've created some sort of potential unintended consequence with air quality and combustion safety in your house.
Mm-hmm. Yep.
okay, two different things. Or let's take air quality. How are we attacking air quality? How are we making sure the air we're breathing is safe?
With an older home, we really didn't need to do anything. They were just leaky. Air would leak in at the rim joists, around basement windows, around for upper level windows. It'd leak in all over the home, and air would constantly be changed out. And even if air didn't want to move through there, through, say, the stack effect or fans running, you still have your heating appliance. It's going to use a lot of air for combustion and a lot of dilution air. When I say combustion air, I'm talking about the air that mixes with fuel and it gets burned. And when I say dilution air, I'm talking about air that just goes up the vent following the warm air.
Is that also known as ventilation?
No, it's a different
It provides
type of air.
ventilation, kind of indirectly.
Yeah.
Okay.
For the
yeah,
house.
not intentionally.
Not intentionally. Unintentional ventilation.
It's unintentional ventilation caused by your fuel burning appliance that's using air in the room to support combustion. So that's going to pull a lot of air through the home. That's air that's always leaving. And for every cubic foot of air that's going up that vent, and which oftentimes in older homes, it's going to go into the chimney. You see all that stuff coming out of the chimney at the top. For every cubic foot of air that's leaving, cubic foot of air is coming back into the home somewhere, somehow. It always gets replaced. And it means you have a lot of natural ventilation in the home. So you don't end up with stale air. You end up with a lot less problems. You don't end up with moisture issues. You talk about old homes and how they tend to really dry out in the wintertime. Mm-hmm. It's because you're constantly replacing that warm, moist air with dry, cold outdoor air. It dries a house out really well, and it makes your house really durable too. I mean, we talked about that at the last episode about what makes a house durable. This is a durable home.
Yeah, my humidistat in my bedroom this morning, I looked at it, was 21% humidity.
Whew,
sure.
Pretty dry.
Yeah,
pretty
old
dry.
house.
And that was after sleeping in it all night.
Wow. Yeah.
And so you take a new home, and now we're trying to button these walls up as much as we can so we don't have air leaking through it. But then we've also removed that heating appliance that pulls air through it all the time, because we've replaced those now with high-efficiency furnaces that don't depend on indoor air for combustion. A lot of the time, it's going to be a two-pipe system where it takes the combustion air directly into the furnace from the outdoors. I'm doing a lot of hand movements for this demonstration here.
We should put a picture of a sealed combustion furnace and the notes on this.
That's a good idea.
So people
we'll do
know
that.
what it looks like.
So it's taking air directly from the outdoors, mixing it with the fuel, and then pumping it right back to the outdoors. It never communicates with the air in the home. So now we don't have this natural air exchanger that we used to have, an accidental air exchanger.
Yeah.
Can I ask a funny 8097 question? So explain what that means in terms of 1 gallon of natural gas on an 80 versus 1 gallon of natural gas on a 90 versus 1 gallon of natural gas on a 97. What does that mean for me, the consumer?
Well, it doesn't really matter how much gas you're using. All it means is however much available energy you have, the percentage tells you how much gets converted into heat for your home. So if it's 80% efficient, it means 80% of the energy in that fuel heats your house. The other 20% goes up the flue. It rises up the top. That's what you see coming out of the chimney is 20% wasted heat.
Okay. So in my thought process, a gallon delivered, 80% of that gets turned into heating your house and 20% just gets turned into a byproduct.
That's right. 97%, you're only wasting 3% of that available heat.
Okay.
Side note, people like to kind of make a big deal about electric furnaces and electric heating appliances. Like, that's
They're
100% efficient.
Yeah.
And it's true. They really are.
Yeah.
100% of the electricity is used to heat the home. It's converted. It's all converted into heat. It doesn't mean it's a better appliance. It doesn't mean that this is a good use of electricity. That's talking about the electricity at the appliance.
Yeah.
How much was wasted to get that electricity to the home?
Yeah.
I mean, what are we doing to generate that electricity? We're burning
coal.
Fossil fuels?
Yeah.
Coal? Yeah.
Probably. But it's also, electricity is more expensive than natural gas here. So it's just, it's cheaper to use natural gas.
Yeah.
Sure, it's more abundant. So then these appliances obviously have something to do with comfort and moving this air. You talked about that.
Yeah.
Air movement.
Yeah,
is...
unintended consequences. So air quality and then combustion safety, which if you take an old house and you do these changes to make it more energy efficient, more comfortable, like air sealing and insulation, and you don't address the ventilation systems, you might have problems, like Ruben said, with moisture and all of that in your house. But you can also have problems with combustion safety, meaning let's say you've got a water heater that is a natural draft water heater, which is what most people have. It's, if you go down your basement, you look at your water heater, it's that big tank that stands there.
We're going to take a quick break, and then I'm going to let you talk all about combustion safety when we get back. It's really exciting and interesting. You've been listening to Structure Talk, a Structure Tech presentation.
Hi, everybody. Ruben Saltzman here with the Structure Talk podcast. We talk a lot about education on our podcast because this is one of our core values here at Structure Tech. To prove how important this is to us, we actually teach free continuing education classes to real estate agents all over the Twin Cities. We've been doing this for years, and we have classes ranging from 1 to 4 hours in length. These classes are taught by both me and Tessa. And if you're interested in having us come out to teach at your office, all you need to do is visit our website, click on the Education tab, and you can see instructions on how to get us out to your office. And you can also see a calendar of upcoming events. If you're interested in having us come out, please visit our website at structuretech1.com.
Welcome back, everybody. You're listening to Structure Talk, a Structure Tech presentation. And as we were going to the break, we got on this combustion safety idea. And, you know, when you've got gas burning appliances in your home, you want to make sure that any byproducts that are being generated are finding their way to the outside. So from a building scientist's perspective, I know you've got concerns about how that happens.
Yeah, a lot of people, you know, they might do those energy efficiency improvements first. Like they'll do the insulation in the attic first, you know, because they're aware of that. They want their house to be cheaper to heat and cool and more comfortable. So they'll do the air sealing, they'll do the insulation, and they won't think about how that impacts their water heater or their air quality. And so a lot of houses have natural draft water heaters. Natural draft water heaters just rely on the heat from the exhaust gas to rise up and out of that flue. There's typically a gap there between the actual water heater tank and the flue. And if you have a strong enough negative pressure in the house, it can actually suck those exhaust gases out of the flue and back into the house. So if you make a house a lot more airtight and you change the pressures in the house, let's say you air seal the attic, let's say you add new windows, your house is a lot more airtight. Let's say you install a new bath fan in your bathroom because now you've made your house more airtight and you've got, you know, moisture issues and air quality issues. You install some bath fans. Those bath fans suck air out of the house. They can create a negative pressure. All of those things combined can cause your water heater to now backdraft where it didn't used to backdraft before.
So backdrafting is just the pollutants are staying in the home. They're not finding their way up.
Exactly. And there's carbon monoxide and water vapor and all sorts of things that are not safe to that you don't want to be breathing in, venting right into your house.
Fun stuff. That makes sense. I mean, it's why my city made me put a fresh air intake after adding spray foam insulation into my attic. They're like, you have now made your house tighter than it was before. Now we're going to make you put this
6-inch hole in your wall.
It was larger than that because we had some mother load hood vent.
Oh, you added one of those too.
1200 CFM.
Yeah.
Do you have a powered like makeup air that heats the air, or is it just a passive intake for combustion air?
It's just passive.
Just
intake.
a passive intake.
Yeah. I'm kind of poking fun at myself here, but it's only a 600 CFM fan, so it's the smallest, but yet it's still triggered this.
Well, and I've seen that where people remodel old houses, they put in a massive hood vent in their kitchen, and they don't do any sort of combustion makeup air for the furnace or the water heater, and that water heater now backdrafts.
Well, I wasn't going to do it either until the city told me I had to do it.
And you know what? In some houses, adding that makeup air sometimes isn't enough to prevent that water heater from backdrafting. It can still backdraft even with makeup air.
Yeah, this formula is not magic. The formula doesn't take everything into account. It's just saying, this is probably pretty good.
Good enough, yeah. But the only way to know for sure is to do some testing. There's testing, what is it called? CAS testing, where you basically do like a worst case depressurization test on your water heater to see if it can draft okay when all the windows are closed and all the exhaust appliances are on. And you do that test. But it depends on outside temperature and wind and other things that can impact it.
So does CAS stand for something specific?
Yes, combustion appliance zone.
Oh, so
I had
it's a
to
Z,
I had
not
to,
an S.
Yes,
Okay.
I had cobwebs. I had to scrape them off. But yeah, I used to do a lot of that testing when I worked for a local nonprofit doing weatherization stuff. We used to do that a lot in houses. After we would do the air sealing and do the ventilation part, then we would test the water heater to see if it would backdraft, and a lot of times they would. And sometimes
I was going to ask you what your failure rate was.
a lot of the time.
Even at Structure Tech, that's something that we do on all of our home inspections. And it's not quite the exact same thing that you would do, but it's really darn close.
Yeah.
I mean, at the beginning of every home inspection, we go around, we close all the doors, all the windows, make sure it's all closed up. We turn on all the exhaust appliances, bath fans, kitchen fan, clothes dryer, everything removing air from the home. And when we remember, we even turn on the furnace's blower fan, which can affect pressures in upper level versus lower level. And then we do check the draft on the water heater and make sure it's drafting properly if it's a natural draft water heater. And we find a lot of those at backdraft.
Yeah.
And then, we could just stop there and say, it backdrafts, have somebody look at it, but we'll always take it one step further. We go open a basement window or a door somewhere, and if it instantly starts drafting properly, boom, we got it. We know what the issue is. It's insufficient makeup air. It's not a problem with the vent. It's not a problem with anything else. If you open a door and it starts working right, That's combustion air. It's real simple. And it's nice to be able to give people a clear answer as to what this issue is instead of find somebody else who can get to the bottom of it. And the next person may or may not be able to get there.
If opening a window doesn't fix it and it's still backdrafting, usually the best solution to that is...
Power vent water heater.
Yes, replacing that water heater with a different type, one that's a power vent.
Yeah, and that's going to push the exhaust gases right out the side of the home. It doesn't really care if you have negative pressure or not. It's still going to work.
Well, we'll let you geek out on different types of water heaters at a different time. Okay.
Can't do it now, huh?
No.
Can we do it after the show,
okay,
Tess?
sure.
All right.
You've been listening to Structure Talk, a Structure Tech presentation. Thanks for listening, everybody.
For more information on how we can provide you with the right information about your home before you buy or sell, contact us at structuretech1.com.